So we've looked at solid rockets and hybrid rockets. Let's take a look now at liquid rockets, which really are a 20th century invention. It was early in the 20th century that Professor Robert Goddard, who was working at Clark University in Worcester, Massachusetts at the time, developed the concept of liquid rockets. The liquid rocket would carry its own fuel and oxidizer, and you could control how much of that went into the rocket engine, ignite it, and the rocket would take off. Professor Goddard actually appreciated, in a way that few people did at the time, the capabilities of rocket engines, because he realized that since they carry their own oxidizer, they don't need to operate in the Earth's atmosphere. And in 1919, he published what he thought was just a simple academic paper explaining how his engines work. And he postulated in that paper that with a sufficiently powerful rocket, you could actually leave the Earth and fly all the way to the moon in 1919. The New York Times somehow or other came across this scholarly article, and they really pounced on the poor physics professor. This was in January 13th of 1920. The New York Times editorial said, "Space travel is impossible because without an atmosphere to push against, a rocket simply cannot move so much as an inch. Professor Goddard, it is clear, lacks the knowledge ladled out daily in high schools about basic physics." Of course, July 20th, 1969, about 50 years after Goddard published his article, the Apollo 11 astronauts landed on the moon, and I'm happy to say the New York Times did publish a retraction. The Times said, and I quote, "Further investigation and experimentation have confirmed the findings of Sir Isaac Newton in the 17th century, and it has now been definitively established that a rocket can function in a vacuum as well as in an atmosphere. The Times sincerely regrets its error." So it goes. So here's a very simple conceptual diagram of how a liquid rocket engine works. As I pointed out before, you need a fuel and an oxidizer. They're carried in their own tanks, and then pipes take the fuel and the oxidizer to a combustion chamber where they are ignited and they burn, and then hot gas comes out the back, and that makes us go forward. And that's basically how a rocket engine works. This is simple. We call it a pressure-fed rocket engine. Obviously, you need something to push the oxidizer and the fuel into the combustion chamber. And inside the combustion chamber, of course, things get pretty hot. This is the inside of a combustion chamber. You can see what we call a shower head, and the fuel and the oxidizer are pushed through those little holes where they sort of get pre-mixed, which helps the combustion. And actually how you design those shower heads, which are formally called injector plates because you use them to inject the fuel and the oxidizer into the combustion chamber. The combustion chamber is inside here, and all of this area is the rocket nozzle, which we'll talk about shortly. You can imagine that the pressure when you start burning the fuel and oxidizer inside this combustion chamber gets pretty high. And if all you have is to push the fuel and oxidizer into the combustion chamber using pressure in those tanks, that pressure is going to get pretty high, which means the walls of those tanks are going to have to get thicker and thicker to hold the pressure, and it runs away. So you can use pressure feeding for rocket engines that are relatively small, but if you want to get a lot more power out of it, then you need a better way of getting the fuel and oxidizer into the combustion chamber, and to do that we use pumps. So the critical part of almost any liquid rocket engine is a turbopump to get both the fuel and the oxidizer into the combustion chamber. So now we don't have to have high pressure inside the oxidizer or the fuel tank, because the pumps will create that pressure to get into the combustion chamber where it gets burned. Just to give you an example of how powerful these pumps have to be, the high pressure oxygen turbopump in the Space Shuttle main engine It's about the size of a large automobile engine, maybe, you know, a V8 engine in a Cadillac or something. And yet it puts out 50,000 horsepower. Man, I'd love to see what my car would do with a 50,000 horsepower engine in it. Well, maybe I wouldn't. But in any case, that's what you need to pump enough propellant into the combustion chamber in a really powerful rocket engine. So this is a picture of the F1 engine. You can get some sense here of how big the turbopumps are to pump all the oxidizer and fuel into the engine. Now, the other characteristic of every rocket engine is it has a nozzle on the end of it, and you may be asking, well, why do you need this big nozzle? It's heavy, I mean, it creates drag. Well, here's the thing. The trick with a rocket engine is what we call controlled combustion. So first of all, we don't allow everything to burn at once, like in a stick of dynamite. In the combustion chamber here, we start out with a very high temperature and pressure. What we really need to do is run the combustion products through what we call a converging, diverging nozzle with a thin throat in the middle. This is the throat. And when the randomly moving molecules go through that throat, they actually get up to a supersonic velocity, and this random thermal motion is converted into a directed kinetic energy where the random motion is pretty much removed, and there may be a little bit of motion side to side, but most of the kinetic energy is now directed backwards, and that is what gives you your forward thrust. So we'll just finish up with a look again at one of the examples of the biggest liquid engines that were ever built, and those were the engines for the space shuttle, which were also the first large fully reusable engine. And here is the fuel tank. We call it an external tank because it was so big we couldn't put all the fuel we needed inside the shuttle orbiter itself. And of course, it's huge. You can look at the people down here at the bottom. You get some sense of how big it is. And this is the tank when it was being manufactured in Louisiana. And you can see here the hydrogen tank for the liquid hydrogen and the liquid oxygen. Liquid oxygen is much denser than liquid hydrogen, so it doesn't take up nearly as much volume. So most of the external fuel tank for the shuttle was for the hydrogen. And now that we've looked at how liquid engines work, let's put it all together and look at a space shuttle launch where, of course, in addition to the liquid engines, which ignite about 6 seconds before the solids, they come up to speed, and they don't have quite enough thrust to get the shuttle off the ground. That's why we have the solid boosters, which have just ignited, and now the whole stack lifts off on one of the shuttle's many successful missions. But we need to find out how much we can get out of a limited amount of propellant that we can carry on board. And that is what we'll learn about in the famous rocket equation, which we'll cover in the next segment.